Hello class, welcome to our next chapter, chapter 7. We're plugging right along here. This marks a little bit of the halfway point of our semester, considering we do 4, 5, 6, 7, chapter 10, and then chapter 11, so you're over the halfway mark. I need to do my math a little better on that one, I suppose. And our first section in this chapter just talks about the basics of what it means to be a function. So I'll just kind of I'll show you the screen here. You can pause, you can write it all down. I don't always write down all of the vocabulary because it's in your online version of your textbook, but I'm trying to kind of switch that official math language into everyday language, so hopefully this will help you understand what these definitions are all about. So, a function, for each input there is exactly one output. Said in a different way, kind of unofficially, x's don't repeat. You cannot have x's that repeat, meaning you can't plug the number 2 into a function and get 5 on one day, and then plug a number 2 into the same function and get negative 17 on a different day. It has to have a little bit more consistency than that. Every time you plug in, say, the number 2, you would expect the answer to be the same output. And so, oh, I did write it right here. Great. So the domain is the input values. It's also known as your independent variable. Typically, it's x. A lot of times when we have an application problem, it's time. Time is always an independent variable given the choice. And the x's can't repeat. Your range is just the opposite of all of that. It is the output values, it is the dependent variable, and typically it is the y values. So when I am thinking of just a basic xy coordinate plane, the x's are the domain and the y values are the range. Okay, and again, in application, it can be any letters. The letter is insignificant, but typically we think of them as x and y. All right, notation. We usually use function notation. It looks like this. I'll show you some examples of that as we move through our lesson. And you read this as f of x. It is not f times x. This is not, it looks the same as what a multiplication might look. When it's function notation, it doesn't have the same meaning. Or if you wanted to kind of expand the reading, f is a function of x, and then x is, again, your independent variable. So our first example just shows us all sorts of different ways that we could determine whether or not something is a function. So it's almost a yes-no situation. So is it a function? These fancy little squiggles are used for set notation. So we have 3 coordinate pairs. Oops, it looks like I forgot a parenthesis. We have 3 coordinates in our set number 1 here for A. And so do the x's repeat is basically the question you're asking. Y's can repeat. It is okay for y's to repeat. It is not okay for the independent variable. It is okay for the dependent variable. So if you remember, it always goes x, y. So here are my 3 different x's. They're all different. Yes, this is a function. For B, here are my 3 x's, 1, 1, and 2. So because that repeats, it cannot be a function. This is a different way to look at it. I know you see some of these mappings in the textbook. I assume you see them as well in my math lab because it's supposed to be a match. But you can tell that if these are the x's, there's no repetition because x goes with -1, 2 goes with -1, and 6 is matched with 0. If that's confusing to you, write it down as a coordinate pair, kind of what you're seeing here. I'm seeing 1, -1. I'm seeing 2, -1. And I'm seeing 6, 0. So that is what that mapping is representing. Since the x's aren't repeating, I would say yes, it is a function. I know this is kind of maybe beating a dead horse here, like it seems like we're going over and over and over and over again, but I just want to make sure you understand these basic things. So let's look at this one. It looks like 6, -6 is being matched with 4. It looks like -2 is also being matched with 4. And then it looks like 3 is being matched with 2. So you don't always have to go, straight across there. And so again, 3 different x's. Yes, it is a function. Perhaps I should have used one. I'm sure my intent when I wrote this is to make this one not work out. I can throw additional problems up here for us. So we can look at it as a coordinate pair situation. We can have this kind of mapping, or you can have a graph. And so when you're looking or given a graph and the question is it a function? You're going to do something called the vertical line test. And so you might have even taken a math class in the past where this was familiar to you. So what you do is you take whatever writing, it can be anything. It can be a writing utensil, a ruler. You can just, use your finger. And you want to just hold that vertically. And then you just want to run it along the function. And if you only ever cross that function once, then it is a function, or the line, the graph, I should say, because we're determining whether or not it is a function. So you just kind of run that along, and if you're only ever crossing it once, then it is yes. And so if you think about like the lines that my pen, it's only ever crossing the blue line or intersecting with the blue line once. Let's hold this vertically again. And let's run it along here. And again, if you think about the marks my pen is making, these horizontals, it ever only intersects one spot at a time. So here's an example of yes. Let me give you one example where it doesn't work out so nicely so you can see the contrast. Let's look at something that looks like that. Right here, when you run your vertical held pen and you're looking at where your pen intersects, let's say we're talking about right there, it would intersect in 2 different spots at the same time. This would be an example of not a function. All right, it is going to take me a second to erase all this, so you might want to just fast forward. And I will throw one additional problem up. Let me just double check before I erase all of these definitions that were in recording. I did make an entire video once and thought I was speaking, and it turned out that I didn't hit the record button quite as forcefully as I needed to, I guess. And so then I spoke for a half hour, maybe 40 minutes, and obviously nothing got recorded. All right, so let's do one more like this before I move on. So I'll leave this question up here. Is it a function? So if I have an additional example where it's some type of mapping with these circles, and it doesn't matter what the numbers are. Let's say you have something that looks like this. And we'll take that one to 2. Hopefully you can see that your ordered pairs from this mapping would be 0, 1, 0, 2, and 6, 2. Don't know if you noticed my hesitation there. I was going to attach it to the 3 and then I went a different direction. And so your x's do repeat right here. This would be an example of something that is not a function. All right, so that really does cover all the different types of ways that you might see that. Ordered pairs, mapping, graphs, that pretty much covers everything. All right, there's a few additional types of questions we're going to look at for this one. The next example is to evaluate a function. And I think you'll find that this is pretty straightforward. Maybe I should erase, if you already put the A, so sorry, put the A down here. Find f of 3, and then B, we will find f of a plus 1. All right, so here's our next example. If you're asked to evaluate any function, what you will notice is that instead of saying x equals 3, what you will notice in the notation is that the x is replaced with a particular number or an expression. And so what you will do is it's not going to explicitly say plug in x equals 3, but you now can infer to plug in x equals 3 because you can tell that they've replaced the x with that number. So that's your hint. So we're going to come up here and instead of 3x minus 7, we're going to go 3 times 3 minus 7. And then just work it out. Use our PEMDAS. Please excuse my dear Aunt Sally. 9 minus 7 is 2. How does it look if you have not only a variable and a number? Like, what does that look like? You're going to just plug all of this in. So another word for plugging in, maybe perhaps a more mathematical word, is to substitute x for a plus 1. So again, instead of this x, whatever is inside this parenthesis, it could be a number, it could be an expression, it could be a negative, it could be 0, it could be a fraction. You're going to plug that in. There's no more x. The x goes away. And you substitute in whatever's in the parenthesis. And then you're going to simplify it to the best of your ability. So here, you can distribute that 3, and then you are going to be able to have some like terms to put together. And so you just leave it like that. Because you substituted a variable with an expression with a variable, you would expect that there would still be a variable in your answer. So if you want to try one like this, it doesn't always have to be f. We could name our function with any letter. And I can make it as difficult as I'd like, and so it can have squares and cubes and whatever. And so let's do this. Oh, that's going to get tricky. All right. Maybe not this one. Sorry. You guys just try A. I did realize immediately. This one I didn't have planned in my notes. I just kind of made it up. So you can pause right there and try that. And then I'll give you an easier one to try with the expression in it. So So plugging in -1. Is going to look like that. Make sure you square, this is just really what I wanted to practice. Make sure you square that negative before you multiply it by the 5. So -1 times -1 is 1. 1 times 5 is 5. -2 times -1 is +2, +1, and 5 plus 2 plus 1 is 8. Let's try maybe h of x equaling 3x minus 6, and if you need to find h of w minus 2, you can try that one. What I had originally set up, it was going to mean that you were going to need to FOIL, and it didn't need to be that complicated. And so instead of writing this x, you will plug in w minus 2. And so then you will distribute, and you have like terms, and so your final answer is 3w minus 12. All right, there's a couple more different types of examples you'll see with functions. These I would highly recommend. Because I can't be as accurate as I need to be on this whiteboard, and this is true whether we are virtual or in person. It is hard for me to show you this one, and I would highly encourage you to look in the book. It is example 4. It is section 7.1, example 4 in your textbook. So what happens is that you have your coordinate plane, and you have some type of graph. And so let's say it goes like this. And let's make this -1, -2. And I want this to kind of be at the point 5, 6. I don't think I'm doing it the exact same points as your textbook would, but hopefully you are getting the gist of it. -1, -2, -3, -4. This is the point -4, -3. I am just trying to illustrate, all right? So the instructions say determine the member of the range if paired with +5. And then it says the same thing in reverse, determine the member of the domain paired with and I could even do something. Is there anything else that lines up nicely? I could even do maybe this one here. Yeah, let's do +3. Okay, so it doesn't have to be the ends. That's my point. But again, you're going to have to give me a little creative leeway here. All right, so what are we looking for in A? It says determine the member of the range. So translate that. We're looking for the y value. And if it's paired with 5, that is telling us that the x is 5. So when x is 5, what is y? What is the coordinate? 5, what? And so when I look at my graph, I say, okay, this is x, so this is 5. It looks like my graph goes up and my y value would be 6. So the answer to A is 6. Let's look at B. It says determine the member of the domain. So now we're looking for the x. We're looking for the x value. Think about how that's going to look when I write this coordinate. So this must be the y. So we're looking for the x value when y is 3. Well, your y-axis is the vertical axis. So if I went up 1, up 2, up 3, here is where y is 3. If you go over here and go down, this is what I'm going to, let's make this a little bit more accurate. There we go. When in doubt, just make that line just slightly thicker so it covers more space. All right, and so if you imagine it hits right there exactly and you come down, where am I now? I am at x equals 1, 2, 3, 4. And so 4, 3 is a point on your graph. So you might see ones that look similar to this. I know there's a bunch when we do the online or when we do the textbook homework that I've sent you that additional practice. You do see this. I think it has value because it helps you with some of your graph reading and interpreting, that it doesn't always have to be like giving you the x. I can reverse it. And if I give you, excuse me, if I give you the y value, you can go back and find the x. All right, similar to this, but in a function format with an actual equation. This is our last problem in section 7.1. So 7.1 goes really quickly. So our last example, it starts off with some given function. And it might say two different things. What output corresponds, it's like all these different ways to basically say the same thing, corresponds to an input value of 5, and then what input value corresponds to an output value of minus 35. Okay, so how do we translate one that's that look like this? Again, input is x and output is y. So if they're giving you the input value, you're given x equals 5, it's saying find y, or find the f of x. F of 5, which again just translates to substitute 5 in for the x. So negative 5, plug 5 in for this x, plus 2 more. This is negative 25 plus 2. The answer is negative 23. Here, what input value corresponds to an output value of negative 35. Oh, I think I went the wrong way on this. Please forgive me. Let's switch that to negative 33. That'll work out just a little bit better. All right, so if the output value is negative 33, I'm giving you the y. Or if you want to think of it, I'm giving you the answer and I'm saying find x. So some of us have been kind of conditioned to, like, let's not think of this as a function, cross it out, and think of it as y. I know that's a strategy that sometimes high school teachers will use. And so in any event, you're replacing all of this with that negative 33. So negative 33 equals negative 5x plus 2. Subtract the 2 over. So negative 35 equals negative 5x. Divide, and x is positive 7. So that is the input value is 7. All right, that wraps up 7.1. So kind of shorter, a lot less complicated than so far chapter 6 was. So hopefully you enjoyed the little break of some of the fractions. No fractions today. So take care, everyone.